the last thing that we like to calculate are the displacements. Remember, our bar looks like this. There's the long segment, the smaller one, and that is point C, that is point D. So what we're interested in is the motion of that. That would be delta at C. And then this, which would be delta at D. Now here we've got to be a little bit careful because what we're doing is we're accumulating the various stretches. So we have the stretch in bar BC, that's B again, the stretch in bar CD, and the stretch in bar DE. So we have to make sure that we make the transition, or maybe make the relationship between those and the actual point-wise displacements. Delta C is pretty easy because it's going to be relative to the fixed support. So we would say that delta of C is really going to be delta of C relative to B. And that's just another word for the extension in bar BC. So that one is easy to calculate because we've already got that one set up as part of our earlier stress strain law. So that is, again, going to be P1 L1 over A1 E1. Now that's assumed to be right if it's plus. Remember, we're assuming that it's going to be stretch. So if it turns out to be a negative number, so let's write this down here. If it's a positive number, that means delta C is going to move to the right. If it's a negative number, then delta C is going to be to the left. Why is that? Because we've assumed tension everywhere, and tension moves the bars to the right relative to B. So that's a pretty relatively straightforward link to make between those two. Delta D, though, we've got to be, again, a little bit cautious. What we would say is, so the delta at D, that's going to be delta of D, rewrite that, relative to B, which is delta of D relative to C, just like in your dynamics, plus delta of C relative to B. Well, this one we already calculated. That's actually going to be delta at C. Same thing. Delta of D relative to C, that's also the stretch in bar CD. So once again, we have to watch the sign because if it's positive, it's going like this. And if it's negative, it's going like this. So as long as we keep track of the relative stretches and their signs, the sign is embedded in the sign of P, pardon me. So the sign of the stretch is embedded in the sign of the internal bar force that we have. So again, if the P value is plus, that means the right end is moving that way relative to the left end. If the P is minus, then that means it's going to be moving this way. And what we want to do then when we make our final number is give a value and a direction left or right. So we want, when you practice this on the homework, you want a numerical value and an arrow. You don't want to say plus or minus because people won't know what you're talking about. If you say to the right or to the left, then everybody's going to know that. So the arrow is going to take the place of the sign in this case. So I'll have you work through some of these for practice during the homework, and then you'll get a little bit more comfortable with that. In fact, we'll probably assign one that looks a lot like this. All right, so that takes care then of our first type of statically indeterminate problem. So remember, there are three tools, just as a review, there are three tools of structural mechanics or solid mechanics, and there are three types of problem. So there's 3 and 3, and sometimes I know there's a lot of numbers flying through your head. But what we're doing now is we've gone through the first of these. All right, so the second type, I'll label that as number 2. This is typically called the composite bar. The composite bar has a cross section of more than one material. I'll say of multiple materials. So in the fix case, the cross-section was the same, but we had different segments. In this case, we have a single cross-section, but they're more than one material. Let's show this by example. And this is a classic problem of statically indeterminate axial bar. We are going to look at a reinforced concrete block. So let's say that this is 4 inches by 4 inches. And let's say that we've got 4 segments of circular rebar, and they're all a 1/2 inch diameter. So again, those go this way. So the bars are running down this length, all 4 of them. And let's say that the length of this is 36 inches. So we have concrete with 4 1/2 inch diameter rebar. And this isn't really a great use of rebar. The main reason rebar is used is because, as you'll either have learned already or will learn if you're a civil, concrete is very strong in compression but fairly weak in tension. And so the purpose of the rebar is to strengthen the concrete zones that are in tension. But in this case, we're going to put a block load here of 1,000 pounds. And we're going to assume that that load's evenly distributed. Remember, we did another problem where we had a rigid block on the top. We're just going to say that that 1,000 pounds gets uniformly distributed as if it were applied using some sort of rigid block. So don't think that it's only going to the concrete. So again, when we draw this, what we mean is we've got a very thin, rigid plate right up there, and the loading is on there. So it's basically pushing down the same amount everywhere along the face of the concrete. Now, we won't bother giving some properties of the concrete because what we're really trying to do here is outline the process. And what happens then as we go through this is we see that we do get a resistance force from the concrete that's resisting the 1,000 pounds, but then there's also a force in each steel bar. So let's go through our big 3 and write out how that's going to manifest itself. The statics is really easy. We really don't even need a free body diagram for this class of problem. We will say that the 1,000 pounds goes into 2 parts. The force of the concrete section, the entire thing, plus 4 bar forces in the steel. Now, some textbooks will lump all of the steel together in one. I think that's a very poor idea, and I'm going to show you why shortly. So this would be our global statement of equilibrium. So we have 1,000 pounds. There is 1 block of concrete. There are 4 blocks or segments of steel. So that is our statement of equilibrium. And that's it. You don't have to do anything else. There is no analog to calculating the internal force like we did in the fix bar. B, stress strain. And again, that manifests itself as delta is PL over AE. And so we now want to go to the concrete section and say the delta, the compression or the elongation, but in this case we know that they're all under compression. So the downward displacement of the concrete, that would be this. So it's going down. That is going to be equal to the force in the concrete, FC, times the length of the concrete, that's 36 inches, divided by the area. Now here's where you've got to watch it. The area of the concrete is not 16. You have to subtract out the holes that are made by the steel. So for the area of the concrete, we would have 16 minus 4 bars that are pi d squared over 4. So pi over 4 times the diameter squared. So that is the area of 1 bar. So the area of 1 bar. So that would be the delta of the concrete. Delta of the steel, that's going to be the force in 1 steel bar times its length divided by the area of one steel bar, that's pi over 4 times 0.5 squared. And then, oh, I forgot the E of the concrete, didn't I? E of the concrete, which will be given. We'll put that as a parenthetical. And then this one will be E of the steel, which will also be given. So there they are. Those are the stress strain laws. That's the delta is PL over AE for those particular segments. Now notice the force in one bar is going to cause the displacement in one bar. That's the way that we've constructed this particular problem. Now here's what's nice about this particular problem, the statement of compatibility. And that question asks, how much of the displacement of the steel is related to the displacement of the concrete? And basically, they're the same, because if we've got that fake rigid plate like so, then the whole thing moves down the same amount. So the delta that we get is the delta in the concrete, which is the delta of the steel. So that statement is compatibility now for the case of the composite bar. The displacements are the same. So I'm going to shrink this down. So compatibility is delta C is equal to delta of the steel. So now what? Well, now we take these two and put those in there. We substitute those in. So we have FC times 36 divided by 16 minus 4 pi over 4.5 squared times E of the concrete is equal to force in the steel times 36, area of the steel pi over 4 times 0.5 squared E of the steel. That's our statement of compatibility. So it boils down then to this. Now the rest is just algebra. It may not seem like it. So the rest is just algebra. We're either good at this or bad at this. I guess somewhere in between. But what we want to do is, first off, if we equate these two, we would cross those out, like so. And we would have that FC is equal to, if we bring these guys up, some factor times Fs. So in other words, we take this formula and we write it like this. Then this statement goes back into equilibrium. We have 1,000 is equal to FC, which is whatever factor we have times Fs, plus 4 Fs. And then we can solve. Solve for Fs. And then we can use equilibrium to solve for the force in the concrete. And I know we're a little over. I'll cut you some slack on the next lecture. And then once again, it's off to the races. After we've got the force in the steel, we can have the sigma in the steel is equal to the force in the steel divided by pi over 4.5 squared. Sigma in the concrete is equal to force in the concrete. I'm just going to write it like that, area of the concrete. And then we can use either expression to get the value, the numerical value for delta. So relatively straightforward. I would say that this is the simplest of the three, in my humble opinion. Went way over. I owe you a minute and a half, but now that's it for part C.